Okay, brilliant. So good to see you again this week. I hope you've had a chance to review the content from last week. So again, the order of delivery is that everything that you see under that week is going to be covered in, so not all of it, but the content covered in the following week is going to be from or an excerpt of what you had in the previous week. So basically what you had in week one under the introductory lecture is the stuff that we're going to talk about this week. And the stuff you have under this week's section is going to be discussed next week. So that's the way it works. And you'll probably see about 3 videos, 3 slide decks for every week. It's a manageable amount of content. Just please review it with a little bit of care for the details. If you need to review the videos a few times, if you need to go over them again and again. It's not as much a matter at the moment with the first week content because it's mostly about the background and history of cardiovascular sciences and the diseases. But as we go forward in the semester, it becomes increasingly more important for you to have a perfect grasp of all the details. So if you need to take another look at it, it's short videos, so you should be able to go back and review them again. And I think there's an issue with Padlet in general, and they've changed the system with QM. I've seen some of you have been able to introduce yourselves in the Padlet, but others haven't. And the Padlet for Q&A hasn't been set up yet. So hopefully just keep your questions for the announcement that will actually give you access to the Padlet, and then we'll review them in the next week, which is week 3. We'll review all the cardiovascular questions all together. Okay, but if you have any pressing questions that you want to discuss today, we'll have an opportunity to talk about them in a bit. So again, the section that we started with is cardiovascular engineering biomedical devices for the cardiovascular system, and also materials that are chosen for these devices and implants. And so starting off, we've had an introduction about the fluidics and the history of developing models to understand the cardiovascular system. Now, why is this important, first of all? Does anyone know why we care as much as to spend an entire week about the history and the fluidics? Yeah.
When academics, people learn from each other, so people grow on each other's way, so it's important to understand where our origin is.
Exactly. Yes. So to understand the state of the art, we need to know how we got here. Okay. And specifically about fluidics, why is it that in designing a certain stent or a biomedical device other than a stent, heart valve, a pacemaker, why is it that in the geometrical design of that device and the material selection, we need to have the knowledge of fluid mechanics of the cardiovascular system? What is it about the fluids that's so key in choosing a material that's going to touch and come in contact with that fluid? So this should come from your sort of fluid dynamics knowledge. Any ideas? Why is the fluid interaction with the material important as, you know, us spending so much time? Yeah.
Together, like actually, you said silicon using the words actually can be used in the human body as well. So I relate, so it's going to like.
Okay, so let's take the silicone. Let's say you're using silicone. Why is it that we need to understand the flow profile of the liquid traveling through? Yeah. Okay, so we understand the forces, the pressure distribution, the shear on the material that is encasing that fluid. But why is that important? What does that interaction tell us? Yeah. Okay, exactly. So we want to know if a material would fail under those pressures, under those shear conditions, okay? And we also want to know, even if it doesn't fail, before failing, it has a phase of degradation, where it's gradually going to degrade and abrade and wear away as the flow is actually shearing it. So it's really important to understand the age, the longevity of that stent. How long can it last in that blood vessel? Okay. A lot of these new materials are polymers that are designed to be biodegradable. So we need to know what the profile of the flow is, how much shear stress you have on the wall, to then look at the tables and understand how long it's going to take for it to lose half of its thickness, for example. And this is the same for a heart valve, which is operating under turbulent flow conditions, okay? It can easily lose its leaflets and the ability to deflect, and that's why we usually have follow-up surgeries. So to be able to design that, to understand the material, to choose the proper material, you need to understand the fluidic. That's why the first week, what we're going to do is we're going to understand the circulation system. I want you to all have this sort of a back of the envelope ability to calculate and figure out what those values are in different sites of the human circulation. Now, this is important not just for the cardiovascular system, but also in the respiratory system. In any other system in the body, we always have flow. So flow is key. The exchange with the fluid that's being circulated is key. And these are going to be recurring themes throughout the semester. Okay, so pay careful attention, and if you're not fully understanding a bit of it, please ask me to repeat that, or you know, if you can help your classmates also by guiding the conversation towards those gaps and blank spots. So this is something you've already seen. So and not just in the few video lectures for this week, but also in the previous semesters. As a matter of fact, I have discussed this with you. The diffusion equation that happens in solids, in fluids, in all sorts of media. And what it tells us is that molecules can naturally, passively diffuse through a medium, right? They can travel through other molecules. They can travel through pores, okay? Well, that diffusion can be zero, meaning that they cannot travel at all. They're completely blocked. It's impermeable. Or it can be a rather high diffusion coefficient, meaning that they diffuse pretty fast, okay? Now, the question is, why do we need a cardiovascular system? Why do we need blood circulation? Why isn't diffusion alone sufficient to deliver all the nutrients to the body? Yep. Exactly. So, yeah. Did you want to add? If you what? Diffusion. Okay. Well, I mean, okay, diffusion in general is very slow. Well, even in the cases where you're putting your body under load and you want to deliver something fast, but even in the general case, diffusion is extremely slow. Okay. Diffusion, of course, has a diffusion coefficient associated with it, which has to do with the surface area that you're diffusing the molecule through, with the distance that it has to travel, and with the difference of concentration between the source and drain. But even with these numbers into the equation, you'll see that the times are very slow. So here is a good example for you. So the diffusivity of oxygen, which is the main molecule that we're trying to basically transfer to all regions in the body, in water, which is similar to blood, but a lot less viscous, so it's going to be even slower in blood, as a matter of fact, is actually 10 to the negative 5 centimeters square per second. Now, usually this time, this travel time again, has to do with distance and the diffusivity, or the diffusion coefficient D, okay? So the time that it takes to travel from point A to point B depends on the distance between the 2 points, the L parameter there, and the diffusivity of the medium that we're talking about. And as I said, for water, if you calculate the diffusion coefficient, you'll see that based on that Einstein equation that we discussed before, the viscosity of water taken account of, the diameter of the molecule, all of that will get you that number. Now, imagine we're talking about a 1 millimeter distance. Okay, that's a very short distance for oxygen to travel. It takes about 1,000 seconds for a molecule of oxygen to travel a distance of a millimeter. Now, this is still in the reasonable realm. Now, I'm going to ask you, if we made this 10 millimeters, 10x, how long would that take rather than 17 minutes? If we increase the L by a factor of 10, how much is the T going to be increased? Like, yeah,
1700.
yeah, exactly. So it's going to be 1700 minutes. And that's about, how many hours is that? About 30 hours, right? It's going to take about 30 hours to travel from one end of your finger to the other, about 10 millimeters. That's how slow it is, okay? And we're talking about oxygen, which is one of the smaller molecules. It's the smallest, actually. So I just want you to have an understanding. Diffusion alone, if you're a bacteria, fine, right? It's like, 1 micron, 2 micron, the entire size of the organism. So traveling is pretty far, right? Easily get from one end to the other. But if you're a human being, or even a plant, right? Getting through the leaves of a plant, diffusion isn't going to be fast enough. Okay, so let alone distances across your body of a meter, right? 1,000 millimeters, 2,000 millimeters, right? It's going to take days, weeks to get oxygen from your head to your toe, from your heart to your toe. So it's ridiculously slow. So it's clear that we need to have circulation, okay? The following questions are even more important in us understanding why the circulation system has naturally evolved into this shape that it has, okay? Because it's all a matter of evolution, right? It's gone from a certain geometry, optimized its way through to reach this certain design that we currently have. Now, let's move on to the second question. And before we do that, flow in a pipe. How many of you have already seen flow in a pipe, the equation, the fluidics? So I'm not going to go over the derivation of this equation up there, the Hagen-Poiseuille equation, but basically this is an engineer's quick approach to understanding fluidics, whether it's in a pipe, it's in the human body, whether it's in a car that you're designing, whatever it is, okay? This is one of the most useful equations you'll ever see, and you'll come back and back over and over again to search Google for this equation, okay? And the thing that makes it very elegant is that it deals with fluidics like circuits in electronics, okay? It makes each of these elements, it approaches each of these elements as an element of the circuit. And when it looks at a pipe, it looks at it as a resistance, because it is a resistance. It has a difference of pressure between the two ends, the delta P, very similar to the delta V, the voltage difference between the two ends. And that difference of pressure is exactly what drives the flow. In electricity, it drives current, I. In fluidics, it drives the flow, Q. And it's got the same linear relationship, meaning that if I make the length of this double, the resistance is double, right? If I put two of these next to each other, the surface area is increased, and therefore you'll see an effect in reducing that resistance. So the key thing here is that delta PR, that delta PQ relationship has a coefficient, a correlation factor R, which is defined with this equation, which has to do with this parameter, the viscosity of the fluid that's carrying through. And as it becomes more and more viscous, you can imagine that the resistance is going to increase, right? This resistance is the drag force is the friction that's being applied to the fluid as it's traveling through the pipe by the walls of the pipe. Okay, so if you increase the viscosity of the fluid, you're going to have more friction, you're going to have more loss, you're going to have more resistance. If you increase the length, it's going to increase the resistance linearly. If you increase the diameter or the radius, it's going to reduce the resistance by a fourth power of that radius. Okay, so you hopefully understand the correlation with each of these, but the exact equation, I'm not expecting you to be able to derive. We're going to use it as a tool. Okay, that's something that you probably have done or are doing in fluid dynamics. Now, let's use that equation a little bit. So we've got the resistance, which is this equation here, and we're going to keep in mind that the core equation is delta P equals R times Q. Very much similar to delta B equals R times I. Okay, so that's the basic equation that we're going to be using. And in all of these cases, the resistance there, I'm going to repeat here just so that we have a record of it, is 8 UL divided by pi R to the fourth power. Don't forget it's the fourth power. Okay, so now the question is, why do we have such a huge variation in the sizes of our blood vessels? So why don't we? Okay, so first of all, which of these sites, all the way from the aorta, which is that large, huge, gigantic branch that comes from the heart, all the way down to the arteries, arterioles, capillaries, which are the finest, which are a fraction of a hair in thickness, which of these are most effective in exchanging molecules? Yep. The capillaries. What? It's got a very short diffusion pathway. That's correct. But how do we figure out how much better it is than, let's say, the arteries or arterioles? The resistance. The resistance is one factor which tells you how fast the flow goes or how much pressure loss you get. But how do you work out how much contact you have and how these two compare? Let's say the big aorta with the capillary. In terms of the surface area for diffusion is what I'm talking about. Yes, we can work out the surface area. More importantly, we need to work out the surface area to volume ratio. This is how efficiently an object exchanges molecules on its surface. It's the relationship between surface area and the volume, not just surface area alone. It's this ratio that matters a lot, because it can be a bulky object. It's got a lot of substance in it, but it's limited to this surface, versus a tiny object that diffuses very effectively because the ratio of that surface to the amount of material to exchange is a lot higher. Now, can you tell me, if we have a cube here or a sphere, right, and we reduce the size of that object, how does the surface area to volume change? So I'm making the sphere smaller and smaller. Yep. It increases. But does that correlate with the size squared, the size to the power of 3? So let's say we talk about the sphere, and this is little r, and bigger. Yep.
That's cute.
The cube. Okay. Any other theories? It's this equation. You just have to calculate this. What's the surface area of a sphere? Surface area of a sphere. What was that? 4 pi r squared. What's the volume? Huh? Yep. What was that? So these two cancel out. You only have a single, so it's only linear or inverse linear, right? So the relationship is a constant C, which I don't care as much about, but 1 over R. So if you increase the radius, of course, you're going to decrease the surface area to volume ratio. If you decrease the radius, you're going to increase the surface area to volume ratio, which is what we need. So smaller spheres, smaller objects, this ratio is going to be larger. Okay? But this is important. It's just the first power. It's not the square. It's just the linear. So it's 1 over R. Okay? So now the question is, if the capillaries are such efficient carriers, okay, they're about, you know, do we have them here? Yeah, about a few microns, okay? Here it says about, you know, 30 something, but even smaller actually. But anyway, so no, it's actually 3 10 to the negative 4 centimeters. So that's about 6 microns. So why is it that we don't just use capillaries all the way from the heart down to the organs? Yep. Okay, so she thinks the capillaries would break, so they wouldn't withstand the huge pressure from the heart. That is correct, actually. Capillaries can only withstand a certain pressure, but let's say the material there was designed so that they could withstand the pressure. Okay, yeah. You go first. What did you do?
It's much higher resistance.
Resistance, a much higher resistance, and then what?
More energy.
More energy dissipation. What would you going to say?
I was just gonna say, there is something.
So flow rate, we'll get to that in a minute. We'll get to flow rate in a minute, and we'll compare that. But the energy argument is what is happening. That's what has guided evolution. Is using minimum energy possible. Is optimizing your resource. Because if you use capillaries all the way, the resistance, I know it's, you know, orders of magnitude, 10 to the 6, thinner, smaller in diameter than your aorta, but it comes with a big exception that then the resistance is also going to be, wow, 10 to the 24 more, right? That's massive. Very resistive. It's going to become very resistive. That's why it's going to build up such pressures that it's going to break the vessel, no matter what material you use. We don't have a material actually in hand as of now, even, you know, even with the technological advancement that we've had so far, that can resist 10 to the 24th of the pressure at the outlet of the heart that the aorta is currently able to handle. So the burst pressure becomes an important parameter. The burst pressure, how much pressure to pop something and break it in a lot of these devices that we design. So does the loop or the hoop strength, the strength of the objects to withstand that pressure. And so does the resistance of that design that you have to flow. The dissipation. Ultimately, this is also going to heat up the object that you put there. So that energy is going to be dissipated by also heating the fluid and the object. And that also increases the amount of loading or fatigue on the stent. And that's gradually going to change the performance of the stent. If you change the temperature, the operational temperature, it's going to change the performance of your stent, and it's going to wear away faster. This is why it's so important. We'll give you a design selection table and you'll be able to choose this stent is right for this patient, or this heart valve, or whatever, or this material. So, yes, absolutely. It's those energetic considerations that lead to us using different sizes of blood vessels. Now, I don't know if you've already grasped the difference between the veins and arteries, but apart from the fact that one is bringing the blood back to the heart and one is pumping it out to sort of like carrying it out as it pumps it to the other organs. But what else do you think is different between the veins and arteries based on what you've heard so far mechanically? Yep. So yes, they carry, so the arteries carry the oxygenated blood, the veins carry the deoxygenated. Yes, that's one thing, but yeah, any other, yeah. It has a bit more energy, it has a lot more pressure. Yes, they do need to have a different composition. That's correct. You want to?
Yeah, I was gonna say that veins here which has lower fatigue cycles, so it's not as important for the resistance.
Yes, yes. So arteries always have a greater amount of loading on them. They have to have more resistance. So can you see this in the design of the cellular tissue? Veins are much thinner, a lot more epithelial cells and endothelial cells. The middle tissue is much less thick. That muscle layer, the smooth muscle layer, is much thicker in the arteries, which is also, arteries are part of, this is part because they are resisting higher pressures, but it's also because they actually don't need to have any active pumping effect, as a matter of fact. They don't need to expand as much. Okay, they're pretty rigid. They just need to withstand the pressure. Whereas veins have to be deformable a little bit. They have to have thinner walls so they can expand. Now, you'll see that veins also act as a pump. Veins help the blood that's deoxygenated get back to the heart because it's lost so much of its pressure. The veins actually have their own pumping mechanism that can actually allow for that to a little bit of assistance to get the blood back. And they also have the, anything else that you can spot here that's different between the two? Yep. Valves, yes, yes, valves. Were you going to say the same? Yeah. So valves. Why do they have valves? Why do the veins have valves? Yep. Backwards, exactly. That's exactly right. You see the design is very much like a heart valve. And the idea is it's a one-way valve. It can easily open this way, but on the other way, they're going to basically pressure behind the valves is going to push them together, avoiding any backflow. And that's because as it cyclically pumps through, you don't want to lose the pressure that's built up, the amount of fluid that's been displaced. You want to sort of give it a little bit of an assistance. And these are perfectly designed. The amount of pressure it can pump, the amount of valving action it has, just enough to cover that distance to get back to the heart. Of course, until the person's cardiovascular system can take care of it. After that, we have implants that are just valves. We can implant vein valves. We actually have vein valves that can be implanted to increase that amount of unidirectional flow. So if we compare a rather rigid blood vessel that we just saw has a linear relationship, delta P and Q, with something that deforms a little bit, like the veins, okay? These guys, because they're deformable, they have a capacitive nature. The capacitive nature means that just like the heart has these different phases where it's expanding, it's as a just like a capacitor accumulates charge, and the derivative of charge over time is current. Here you accumulate volume of fluid, and the derivative of volume over time is the flow rate. So it's basically, as it expands, it's sort of like a capacitor. It's storing that fluid, and it's also changing its resistance. So unlike the linear relationship that you have between delta P and Q in a resistor, in a capacitor, the resistance changes. In a capacitor, it can go like this, where your resistance increases as it becomes stiffer and stiffer as it reaches the extreme of how much it can stretch. It becomes stiffer and stiffer. Okay, but at the same time, it can go the other way, or it can go combination of those. You can have complex behavior because it's not just about a single expansion. It's about once it's expanded, how much has the other stuff changed? It's not just the diameter. It's about the stiffness of it, as well as the diameter, as well as the effective fluidic regime. It could go from laminar to turbulent just because of that increase. So it's a very complex thing. I don't want you to understand how these change, but I just want you to know that in the veins, you have a rather non-linear behavior, and therefore also volume changes as you change pressure. So moving on from the differences between those two, the differences give us one key fluidic understanding, which is very important. If you look at this, and this may look a little bit complicated, how many of you have found it difficult to understand what any of these sort of wiggly frequency domain curves mean? I mean, I personally found it very difficult, but hopefully it will make more sense in a little. When the blood flows out of the heart, okay, it's got a certain shape to it. That's one pulse, okay? Your heart beats a second or a fraction of a second, okay? It beats and it sends that pulse. The pulse travels through your blood vessel. It's not an isolated pulse. The next one's coming after. So you can see different pulses, but as they travel through down to your capillaries, this pulse, which is sort of shaking or vibrating the walls of the blood vessels, is going to be damped because of the elasticity of the blood vessel, right? They have the ability to damp this. Now, when it comes to the first direction, which is the aorta all the way to the arteries and arterioles, the oxygenated blood direction, these are pretty rigid walls. They don't have that capacitive behavior you saw right now, right? They're pretty rigid. They don't have that flexing elastic behavior. So it travels through pretty well. You still have the pulse until you get down to the capillaries, which are really thin. At the capillary level and beyond in the veins, that completely dies away. So that pulse that you have all the way at the beginning of the aorta is going to diminish as it travels through the circulation, as it damps through all those elastic walls and the capillaries, which turn the flow into a laminar steady flow. It's then all gone away, which is good, because when it reaches our organs, you have a rather uniform, nice and steady exchange, rather than a bumpy oscillatory cyclic one, which isn't really ideal. It puts the tissue under a lot of strain. So that's the reason it looks a little bit weird, is that the pressure drops, but the pressure itself has a riding sort of oscillatory beat to it, which gradually diminishes as it travels through. So this is actually, this curve is just the pressure distribution all the way from the aorta, and it gets all the way back to the heart and the vena cava. And what you can see here is the pressure drop. So when they say it's like, 12/8, the minimum maximum pressure, the blood pressure of that person, they're talking about this band. And this band gradually, again, it oscillates and diminishes. Does that make sense now? Okay, cool. It's an important curve to understand. A lot of the content we talk about here, for myself, it was a lot of confusion to get what's going on here as a mechanical engineer. But, now it makes a lot of sense. So now let's answer the final question. So the third and most important question is, okay, we know that diffusion alone doesn't work. We need to have bulk flow. We need to have flow. We know that capillaries are not enough for the entire system, so we need to have that branching tree-like structure. The question is, if we branch down to smaller vessels, the surface area to volume, of course, it's much better. Okay, you get a much higher surface area to volume, but it also spends less time in those regions. Why is that? Bernoulli's equation. As you get good. So as you reduce the diameter or reduce the surface area, what happens to the speed? Increases the speed. So it's going to speed through this section with a smaller diameter. It's going to speed through those capillaries, and therefore the dwelling time, the amount of time it spends, is going to be less. So although we've increased the contact, but we've actually fed it through, so it has less time to exchange stuff. So we need to now, as the last check, to fully understand the evolution of this vasculature, we need to verify that the capillaries, if we cut them and put them all together, all the cross sections of the capillaries, they're going to still be larger than the cross section all the way at the beginning in the aorta, meaning that not only do we increase the surface area to volume, but we also slow them down. Okay, so if we figure out that all those capillaries together are going to collectively give us a cross-sectional area that's going to be much larger than what we started off with, that's going to ensure us that we've also slowed it down in that capillary region, which we need to do that. The blood has to be in contact for quite a while. So let's do that calculation. So this one's going to be a little bit of a tricky one. To do that, and now as we do this, I'm going to introduce something called Murray's law, which is also used pretty widely in designing these microfluidic devices, in designing those cardiovascular replacements, in designing in vitro vascular chips, all of that. A lot of these 3D printed or casted tissue mimics that have the vascular structure embedded in them. And these are all designed based on this function, based on this law that we're going to look at in a moment. And they all mimic the actual natural geometry of a tree, or how the fungi grow, or any other microorganism who is trying to increase its contact with the surrounding. It propagates in this certain style. So let's look at this and see how we derive. And the question, what we're trying to achieve is, what is the relationship between the diameter, when it bifurcates, the diameter of the inlets and the outlets? If we understand one bifurcation, we can basically design the entire tree. We can design the entire architecture. If we just understand the bifurcation region, because that's what tells us, you know, how to design this, how to draw it. Now, to answer this, we use the first and foremost, the flow equation, which is the flow coming in that junction should be equal to the sum of the two flows exiting. Does that make sense to everyone? That's a conservation of mass. So, and pretty much a lot of our derivations start from this. And we also use that resistance that we had before. And, you know, you can, if I just expand it, basically, delta dq, and that's the R factor there. So RQ is equal to pressure difference. So nothing new so far. I'm going to look at this term called power. Okay, so this is the energy. Again, we'll talk about energy now. energy that's consumed due to these frictional losses, due to the viscous losses in that channel. And this energy over time, which is power, is the product of force times distance traveled, right, over time. And in physics, you usually do d over t as v, so it's f dot v. But here we just do f dot v over time. And the force required to push the cylinder, there's a pressure acting on this side and one pressure on the other, is the difference of these two pressures, the net delta P times the surface area is how much force you need to push it, right? That's the cylinder of fluid as it travels through the blood vessel. There's a pressure before and the pressure after. If you figure out the difference, multiplied by the area, it will be the amount of force needed to push that forward. So that's the delta P times the area, the cross-sectional area, times the distance over time. Now, if you multiply surface area and distance, the length, it will give you the volume of that chunk of liquid that you're trying to displace, times the delta P over time. And you've seen this if you've looked at sort of piston cylinder equations, the delta P times volume is the equation you use to figure out how much energy. And then if you divide the volume over time, it's going to be the volumetric flow rate, Q. So you're basically having delta P times Q, which is the amount of power required to push this chunk of fluid through a pressure difference of delta P at a flow rate of Q. So basically, this is a key bit of the derivation. And then the second bit of the derivation, so now you can just substitute basically. You can put delta P as what you had there, and you arrive at this equation here. Substitution. And then there's a second term, which is the metabolic energy. Okay, the metabolic energy or the metabolic power is the amount of energy produced by the blood or by the tissue. And this has to do with the amount of cells you have there, or the amount of material, whatever it is, the amount of protein. And that has to do with the volume of the matter that's present there. So this is all the metabolic phenomenon that's happening there. It could be the burning of some proteins, it could be the digestion of some others. And so what's happening is it's producing a certain amount of energy, which is always proportional to the volume. And this is, of course, a constant that has density in it and all of that, but it's proportional to the mass or the volume of matter that is present. Now, if we add those together, that's all the sorts of energy that's being exchanged here. So this overall power is what Murray used to figure out what the optimal radius is. Okay, the amount of energy from both of these sources, and to do that, to minimize this, to minimize the amount of energy, you find the derivative of that over that parameter that you're trying to optimize, right? That's how you figure out, where the zero derivative is, where that peak maximum value happens. Okay, so if you find the derivative of this with respect to r and put that equal to 0, I'll simplify this for you. So this is basically what you arrive at. This equation here, if you take the derivative, so for r to the power of 4, take the derivative of r, it's going to give you r to the power of 5. And then you're going to have the constant times r, because r squared is going to be 2 times r. So basically, it's going to give you something like this. Doesn't matter what the constant is. What matters is that if you simplify that further, you get that the flow rate has to be proportional to r cubed. Okay, it's equal to r cubed times some constant, but we don't care about that. What we care about is it has a proportionality with r cubed. So if the flow rate has a proportionality with R cube, it's going to be the most efficient system with a consideration of metabolic rate of tissue and fluidic losses, inertial losses. At the moment, we're not including any other losses. And this is pretty much the main terms that you have anyway. So this is a pretty accurate derivation, and people have verified it by looking at the geometries of vasculature in the body and elsewhere, and it has worked perfectly fine. So there may be other terms, but they're so insignificant that you don't need to actually include them. Now, if you actually take that and put it up there, you'll see that this is the final equation, is that the diameter or the radius of the inlet, power of 3, so the cube of that, has to be equal to the sum of the cubes of the outlet diameters. Now, this is a very key equation because that equation is the exact equation that helps us answer the question of, are we increasing the overall cross-sectional area or are we decreasing it? So we're almost there, okay? So I know it's been a long journey so far, but just this last slide and we'll be there. So now we've got the tool. We know that the most efficient system, okay, happens when the flow rate is proportional to R cubed. And we know the relationship between the inlet and outlet diameters is D1 to the power of 3 equals D2 to the power of 3 plus D3 to the power of 3. So now the question is, does the cross-sectional area on the outlet side exceed the inlet, or is it smaller than it? Okay, so the question is really, how do these two compare? D1 squared, how does that compare with D2 squared plus D3 squared? These are the area terms, right? So the cross-sectional area is the square of the diameter or the radius. The question is, how does this compare? Is it equal? Is it smaller or is it larger? So this is really the question we need to answer. And if we figure out that these two on the outlet side are actually larger in terms of the sum of their cross sections, then we figured out that we've actually slowed down the flow going from the inlet to the outlet, because the overall cross-sectional area has become larger and therefore the flow has slowed down. Is it clear for everyone what we're doing now? Okay, all good? So if we know this, how can we figure this part out? We know that for the cubes. How do we figure out this for the square? Any suggestions? Yep. Divide it by, well, which diameter? I need to divide both sides, right? If I divide them by D1, then it's not going to be easy to find the right answer. Yep. Yes, basically that's what we're going to do. So we're going to actually take these to the power of 1.5 and then figure out what those extra terms are and sort of see the equivalence of these. So basically what's happening here is we're taking both sides of this equation to the power of 1.5. This side is going to easily become that left-hand side on that equation. This side, however, is going to give us those two terms, but some additional terms as well. Now, what we know for sure is those additional terms are all going to be positive. So they're going to add to these two terms. Now, we don't know exactly what they are, but we know that they're going to be positive terms. because the diameter. So this alone tells us that if you compare these two, okay, on the left-hand side, okay, so you basically have B1 square. You were trying to compare this with B2 square plus B3 square. And what we've done is we've turned that into B1 cubed. So taking these to the power of 1.5 plus some theta. Okay. And what we know for sure is that this part is equal to that part. So clearly, this part is going to make this term dominant, right? Is that clear? So basically what we found is that, working backwards, the cross-sectional area at the outlet side is always going to be greater than the inlet. Meaning that if you then sort of expand this to your circulation system, although these are each individually smaller, but if you put all of your capillaries together, cut them, and compare it with the aorta, you'll see that they're going to have a greater surface area, a greater cross-sectional area. And this is what you see here in this plot. I believe here you're looking at the inverse of that, which is the velocity profile. Yes, the velocity. So the velocity actually does dip down. It slows down as it gets to the capillary level, and then it speeds up a little bit. Not as much as the inlet, but a little bit as it goes through the veins. And that's exactly because of that cross-sectional increase. So, carrying on, this week's content is pretty important. Please review carefully because now we're really getting into the core of it, looking at materials, set designs, other devices, and how we build these, how we manufacture them, how we select the materials, and it's going to get more and more exciting. So this is probably the only bit of math we're going to do in a while, but it's good to just review it. And just because it's a pretty important one, I'm going to post the video online, but please, I encourage you to be here, present in person. And the interaction is the key thing that matters here. We will not post the other videos. We will have Q review though. So please try and make it in person if that's possible for you. Thank you very much.